Okay, so today for the last gravity seminar of the year, it's a great pleasure to have Alex Lupsasca from Vanderbilt University will tell us about the black hole photon ring. Please, Alex.
Thank you very much for the invitation. It's a pleasure to speak with you. And I'm going to take an hour today to tell you about the black hole photon ring, which I hope perhaps many of you have heard of. Maybe some of you even know what it is, but if you have never heard of it, that's okay. This is the talk that's going to generally explain the basics. And I know this is on Zoom. I'm not in the room with you, but I'd rather make sure that everyone understands everything and not go through all my slides than go through a lot of slides and lose everyone. So, this is informal. Please just shout if you have any question, and let's have fun with it. All right. So, the story begins with these observations that have been made over really the past several decades. This is an old story now, this field of black hole imaging. What you're seeing here is a movie that has been made by the experiments listed at the bottom, which is a real movie of actual observations. This is not simulations. This is real data. And you point your telescope to the sky towards the galaxy Virgo, and then you zoom in and you zoom in, and there's this galaxy called Messier 87, which has been known for over 100 years now, and has this jet, which was discovered over a century ago. It's very visible. It extends over a very long distance. And over the decades, a successive series of telescopes have narrowed in on it until finally in 2019, the Event Horizon Telescope managed to resolve the core of this jet, revealing the supermassive black hole at the center of M87. And I'm sure you've all seen this beautiful picture. If you were watching in 2019 the press conference where this picture was unveiled at the NSF, you might remember that the first two questions by journalists were the same question, really, which was, this is great, but it's a little blurry, isn't it? And I remember being a little peeved because if you watch the movie, you realize how many years it took and how hard it was to zoom in this much and take this picture. But it is true that it is a blurry picture. However, the good thing is that now that we know that such pictures can be taken, it's no longer a physics problem to take a better picture. It's an engineering problem now. And in fact, we know that in the next 10, 20 years, it's very likely that we're going to get a much sharper image. And so this poses a pressing question for theorists, which is, what are we going to see? And what is it going to teach us? This is a gravity seminar. Everyone here cares about gravity. There's a black hole in this system. What can we learn about black holes and gravity from such observations? Now, based on our understanding of general relativity, we can predict what we think we're going to see. And the answer is something like this. So this is an image which is produced using something called GRMHD, which is general relativistic magnetohydrodynamics. So it's magnetohydrodynamics is the study of charged plasmas. So you can think of an accretion flow of charged particles that are evolving under, that are producing an electromagnetic field and evolving under its own influence. And all of this is happening in the background of a curved spacetime, which is the Kerr geometry predicted by GR to describe a black hole. And these simulations are very expensive to run. They cost a lot of money to run, but the Event Horizon Telescope has about 40 plus, there's more now in their library. And each simulation describes some kind of accretion flow into a black hole with different initial conditions. And then you can ray trace into these accretion flows to produce series of images or movies. And there's millions of frames of such movies. And this is just one frame from one movie ray traced from one simulation. But the real surprise is that as you look at these millions of images, the details of the accretion flow change because the underlying simulations are initialized with different boundary conditions. There can be stronger or weaker magnetic fields. The particles can flow in different ways. And also there are different electron heating models. So what we think we're seeing is synchrotron radiation from particles. There's a hot gas and particles swirling along magnetic field lines and emitting synchrotron radiation, but there's different details and knobs that you can use to change the details of the emission. But what's surprising and of great relevance to this audience is that no matter what you do with the astrophysics, you can change all those details, but at the end of the day, the images all share this same sharp distinctive feature, which is that there's a very narrow bright ring stamped on top of the image. And that is the photon ring. That's what you're seeing here. And my message to you for this talk is going to be that whatever the black hole, whatever the plasma circulating around the black hole does, that's going to be reflected in the diffuse emission that you see around the image. But because of the black hole, the presence of the black hole itself and the way it lenses light, there will be mirror images of this main emission, which will always be lensed into this characteristic pattern that looks like this ring. And so you should think of the photon ring as the part of the image that belongs to the black hole itself, not to the plasma around it. It's, if you will, it's the signature stamp of the black hole's strong gravity that it adds onto an image. So I'm going to spend the rest of the talk explaining in more detail exactly how this lensing behavior works and why we always see this ring. And then at the end, I'll conclude with some discussion of recent developments on the experimental side. And in particular, I'll mention a real effort that's been going on, which Shahar has been involved in as well, to develop a space mission to launch an orbiting satellite that would enable us to achieve the high resolution that is needed to image this photon ring, and therefore obtain a probe into the strong gravity of the black hole. So that's the overall story, and the rest is details. But the takeaway point is, when you look at black hole images, so far we've taken a blurry image, which doesn't resolve the photon ring. We have not seen it, but we expect that with future experiments, in particular by going to space, which is needed to have higher resolution, we'll be able to actually resolve this very sharp, narrow ring, which is the characteristic stamp of gravity and the signature of the black hole. And the reason this is interesting is because there's a prediction from general relativity and the Kerr hypothesis for the shape of this ring. So we can have a sharp probe of the Kerr metric. And also the shape of the ring encodes information about the black hole, in particular its mass, which is basically the size of the ring. That's what sets the size of the ring. And also the spin, which is encoded in the asymmetry of the ring, which is not a perfect circle. All right, so that's
question.
Yeah, question. Yeah.
Alex, since you already, oops. Let's see if I can get rid of the noise. Okay, maybe now it will be okay. Since you already stated the bottom line, in the actual picture, one could argue that what we see is actually the photon ring. You may say it's unresolved, but you actually see it.
Yeah, so the word seeing is a little vague, but I think we'll agree it's not resolved. And the way I like to say it, and I have a slide later on, so I'll emphasize that when I get to it, is that if you take this image and you blur it, or if you take the same image without the photon ring and you blur it, both are consistent with this image at EHT resolution. And so I think, therefore, we have not detected the photon ring. We expect it to be there because of theoretical expectations. It's a prediction from Kerr and GR, but we haven't tested that.
Could you repeat what the alternative was?
Well, for instance, there are many alternatives, but there's a simple one, which is optical depth. So if you look at the source at lower frequencies, the photons cannot pass through the plasma. And so there is no photon ring at low frequencies. So for instance, it's really important that you go to very high. It's like going to the airport at security. You know, they can't see through your clothes to see if you're carrying weapons, but they pass you through the X-ray. And when they shine high frequency light through you, they can see all the way through. And in the same way, there's an optical depth to this plasma. And at 86 gigahertz, which is the frequency of past observations before EHT, it's not clear that there even is an n equals 1 photon ring that is visible at all. It depends on the simulations. But if you go to 230 gigahertz or higher, there's definitely an n=1 ring in almost all the simulations. And at 345, it's always there. So, one way in which there could be no photon ring in the image is just because there's not enough optical depth and you can't see through to the orbiting light.
By optical depth, maybe you mean that this would be the accretion disk, a direct view of the accretion disk rather than deformed through the geometry of the black hole?
This will become, I think it'll be easier to explain a little bit later in the talk, but to be clear, what I mean is it could be that what we're seeing is a black hole from almost the spin axis. We think we're 17 degrees off the spin axis. So we're looking almost down from above. And there could be a disk, and all we're seeing is a hole in the disk because there's a black hole there. And all the light that we're seeing comes from the surface of the disk, and we're not seeing any light that orbited around the black hole passing through the disk because there's no such thing. There can be no light orbiting through the disk. It all gets reabsorbed. And so in that situation, you're just seeing the top of the disk, and there's no characteristic stamp of strong gravity, and there's no photon ring.
I see. So thanks for now.
Yeah, and that's totally consistent with observations. And not only that, I mean, I would say at the lower frequency of past observations, that would be my expectation, that you're just seeing a hole in a disk and nothing else. And it's important to go to higher frequencies to actually see this effect. All right, so we're getting a little bit into the weeds, but these are really good questions. And let's come back to them in 20 minutes if you still have them.
May I ask a question now about the
Sure.
hole in the ring? Just perhaps you can comment about the black spot, the center of the ring.
Absolutely. So I'm a little bit annoyed because my cursor is not appearing for some reason. Let me see if maybe if I stop sharing and share again. No, okay, I don't know why. So I'm just going to point with my hand. The very, very dark patch in the middle. So in this particular setup, this is a particular configuration in GRMAD called a MAD configuration. And MAD means magnetically arrested disk. So in this particular configuration, what you have are very strong magnetic fields. And the magnetic fields are pushing the matter around rather than the other way around. So there's sort of two big categories of plasmas or accretion flows. There are sane plasmas, which are called, sane stands for standard and normal evolution. And that's where the magnetic fields are weak and there's really an accretion disk of matter flowing, and the magnetic field lines are anchored to the disk and the matter actually pulls the magnetic field along. And then in the opposite situation where the magnetic field is very strong, it's the magnetic field that pushes the plasma around. And the recent observations of Sagittarius star and also polarimetric imaging of M87 strongly favor the MAD configurations. So this is the setup that we think is preferred by nature. There's some slight evidence to say that. And in these situations, the magnetic field pushes the accretion flow close to the equator. So the emitting source, it's not a geometrically thin, delta function thin disk like Novikov and Thorne studied in the 70s. It is a puffy disk, but it's near equatorial. So you can think of it as basically a near equatorial flow. And what you're seeing in this image is this hot gas flowing along the equator all the way into the black hole. And the very dark patch is the contour of that dark patch is basically the intersection of the equatorial plane with the event horizon. Okay, so you have this diffuse background emission flowing all the way into the horizon, and the very dark patch in the middle is the actual event horizon in the direct image. And in particular, the contour is the equatorial plane's intersection with the horizon. And then the photon ring is a little bit bigger, and that's where the light that is lensed around the black hole and orbits around it multiple times ends up on your screen. And there was a bit of a polemic a few years ago about the use of the word shadow, because the word shadow can mean different things. Some people like to think of it as the interior of the photon ring, which coincides with something called the critical curve that I'll get to. So some people call the interior of the ring the shadow, but I think it's more reasonable to think of the shadow as the actual image feature that is completely dark. And in this setup, it has nothing to do with the photon ring or the critical curve. It has to do with where the accretion on the equator enters the horizon. Does that answer your question, or is it too long-winded?
It's a it's a partial answer, but I guess let's wait for the rest of the talk.
Yeah, I'll do my little spiel in the next 30 minutes because I want to respect everyone's time, but I will stay here and answer every question in detail until everyone is perfectly happy. I have nothing else to do today, so I'm happy to do this.
Thank you.
All right, so let me start the story with the photon shell, because that's the special sauce that's going to turn out to explain everything that I've been discussing. So the photon shell is this special region outside of a black hole, which actually has been known for a long time, but is not usually discussed. It's not mentioned in GR textbooks, and even GR experts don't usually think about it that much, but I think it's becoming more mainstream now that it turns out to be important for the photon ring and black hole imaging. And it turns out that the existence of this region is responsible for the photon ring, and its structure governs the appearance of the photon ring. So I'm going to take 10 minutes to explain what this photon shell is. So here I'm showing the Kerr geometry, the poloidal plane, r theta, so I'm neglecting t and phi. And I'm using Boyer-Lindquist coordinates. So everything I'm going to say here is coordinate dependent, but these are the nice coordinates in which to describe this. And the dark disk here in the middle is the event horizon. Of course, if you put phi back in, it's a sphere in these coordinates. And this is the region of no return. So as we all know, if a light ray crosses the event horizon, it can't come back out. But what's less known is that outside of the horizon, there's this shell which has this funny shape. And that region of space-time has the property that within it, it is possible for light to be captured, though not necessary, but it is possible for light to be captured in such a way as to orbit around the black hole at fixed radius. And as an aside for the experts, you can actually take this as the defining characteristic of the Boyer-Lindquist radius. It's the radial coordinate for which bound orbits are at fixed radius. And so if you're sitting in the photon shell with a flashlight, of course, if you shine your flashlight towards the black hole, the photon you emit will cross the horizon and never come back out. And if you shine your flashlight outwards, then the photons you emit will escape out to infinity because they can't escape. They're not in the horizon. They're not trapped. So it's not that all the light in the photon shell is trapped there. In fact, almost all of it is not trapped. It goes through. But what's special about the photon shell is that it's possible, if you aim your flashlight directly upwards or downwards, it's possible to aim a photon on an orbit which is stuck at fixed radius. And Leo Stein on his website, due to symmetry.com, has this really nifty 3D Java applet that lets you play with these orbits in real time. You can animate them, and you can change the spin, and you can change the radius in the photon shell. It's really fun. I recommend it. And the key thing that you can see from the screenshot I took on the right is that these orbits, they don't actually span a sphere. Generically, they go up and down between a maximal and a minimal angle theta. And so throughout this talk, I'm going to use...
Excuse me, can I ask a question?
Yep.
Is it what used to be called in the old days R photon by Bardeen, Press, and Tucholsky? Is there anything that in this photon ring which is not a simple geodesic motion of a photon in a Kerr metric?
Yes, those are the trapped photon geodesics of the Kerr metric. And I think the Bardeen Press Tucholsky paper from 72 studied the circular equatorial ones, if I remember.
Yeah, they studied the equatorial ones, but the generalization to a different Q is trivial. I think everything is in Misnerton and Wheeler.
Yeah, I think the work, as far as I know, is due to Bardeen 73. Yeah. Yeah, I mean, actually, I have some fun comments about that. But let me get back to this in the next slide, actually. I think there's a fun comment about the history of the subject. So these orbits are null geodesics of the Kerr geometry. There's nothing very special going on. But the key point is that as the photon winds around in phi, around the black hole, it doesn't come back into itself because the periods of the theta oscillation and of the phi oscillation are generically not rational multiples of each other. And so these orbits, they actually explore ergodically these shells. And throughout the talk, I'm going to use the word orbit. And by orbit, I'm going to mean a periodic oscillation in the theta motion. So as the photon goes from the bottom in theta to the top and back down, that's one orbit. Or a single bounce from the bottom to the top, I'm going to call that a half orbit. And it's going to turn out that half orbits are the key thing to think about to understand images. Okay, so as the photon goes from the bottom to the top, that's a half orbit, or from the bottom or from the top to the bottom. And I'm going to introduce 4 special quantities. These are the only 4 quantities I need really for this talk, that are called critical exponents. They're called delta, tau, gamma, and mu. And on this slide, I'm going to explain delta, tau, and mu. And then on the next slide, I'm going to explain gamma. So delta is just the azimuthal angle swept per half orbit. What do I mean by that? So as the photon goes from the bottom to the top in theta, how much does it wind around the black hole in phi? That's delta. And this parameter depends only on the geometry of the black hole, and in particular, the mass and spin of the black hole, and the orbital radius in the shell. These are the only 3 things that determine delta. And it's an analytically known function, which you can look up in some of the papers I'm going to mention later. Likewise, the coordinate time elapsed during a half orbit, that we're going to call tau. And it's also, again, a function of the mass m, the spin a of the black hole, and the orbital radius. And then mu is interesting. It's the signed inclination of the orbit. So what do I mean by that? If you look at the innermost shell, the one labeled R minus, well, that last photon that can orbit cannot bounce up and down at all. It has to be in the equatorial plane. And in fact, it has to co-rotate with the black hole because it's always within the ergosphere. So it's a prograde circular orbit. As you go outwards from the innermost shell, the photons start to bounce up and down more and more until you reach this white circle, which is really a sphere, and that's called the photon sphere. And that corresponds to photons that have 0 angular momentum. Now in Kerr, even if they have 0 angular momentum, they're still co-rotating with the black hole. But because they have 0 angular momentum, they and only they are allowed to pass over the poles. So that's the only shell that is actually a sphere. But then as you go outwards, the angular momentum becomes negative, and actually the photons are counter-rotating. And they counter-rotate, but they bounce up and down less and less until you get to the outermost shell, where again you have a circular equatorial geodesic, but that one is retrograde. And
I'm sorry, but I can't help from commenting. You always say a sphere, and I assume you mean constant R.
yes.
But the actual geometry is very different from a sphere.
Yeah, but I gave a disclaimer, so
Sorry.
I said in these coordinates, yeah. And so the photons are initially co-rotating, then they have 0 angular momentum, and then they're counter-rotating. And so sine of theta max goes from 1 at the innermost shell, because theta max is pi over 2. Sine of theta is therefore 1. Then this, and that we're going to call mu. So mu is equal to +1 at the innermost shell. As you go towards the white sphere, it goes to 0 because of the white sphere, theta max is 0. The photons are allowed to go all the way to the pole. And sine of 0 is 0. And then as you go back outwards, sine of theta max increases again towards 1, but because the photons are retrograde, we're going to put a minus sign there. So we're going to let mu go from 0 on the white sphere to -1 at the outer edge. And all I need you to remember basically is that mu is a parameter that goes from +1 to -1 as you go from the innermost shell to the outermost shell, and there's a 1-to-1 bijection between mu and orbital radius. That's going to be important later. Now, at this point, let me say this black hole you're seeing is a Kerr black hole that has 94% of the maximal allowed spin. So the horizon, so if you had a Schwarzschild black hole, the horizon would be at r equals 2m, and then the shell would actually shrink to a single sphere. You would only have the white sphere at a radius of 3m. But as you spin up the black hole, the horizon shrinks in these coordinates until you get to extremality, the maximal allowed spin, in which case the horizon shrinks from 2m to m. But simultaneously, the photon sphere thickens into this shell. And as you spin up the black hole, the shell gets thicker and thicker until at maximal spin, it goes from r equals m to r equals 4m. And here we're almost there. Okay, so I've explained the photon shell, delta, tau, and mu. Are there any questions about what I've said so far?
What are the expectations for the spin of the observed black holes?
We don't know. I mean, there's a lot of theories, but there's really no evidence either way.
Can it be close to maximal?
It's between 0 and 1.
Yeah, it's between 0 and 1. And anyone who
Sure.
tells you they know better is deluding themselves, I think. But one of the exciting things is that I do think if we get space VLBI observations in the next 10, 20 years, we will be able to put actual constraints on black hole spin that are weakly dependent on astrophysics. Right now, you can say, oh, I believe I know exactly what the astrophysical source is, and I'm going to fit my model to the data, and it looks like this spin is preferred. And there are many groups that do this, and they prefer different astrophysical models, and they get different spins. And so, you can get anything. Is that satisfactory or?
Sure.
Okay.
I'm just wondering because presumably you have a reason for showing a 94, A of 94.
Yes, the reason is that there were only 3 spins in the EHT library, and this is one of them. They had they had 0.5 and 0.94, I think, for a long time. So that's innocent. However, there is a jet from M87, which you saw in my little movie at the start. And it is natural to assume, although one should always remember that it is an assumption that could be totally wrong. But it is natural to assume that the jet is aligned with the spin axis. And we do know that the angle of the jet is at 17 degrees relative to our line of sight. So that arrow going off to the top left of the screen is at 17 degrees. And, it's the default assumption is that we're looking down from that angle, but it could be totally wrong also.
But Alex, regarding the jet of M87, I remember that at least some people used to say that it probably indicates relatively high spin. So isn't that true? Or
Well,
it's not really.
Some models that people have studied, the power in the jet has a certain scaling with the spin of the black hole. It goes like a squared. And because the power of the jet in M87 is relatively high, it suggests the black hole spin is high. But I don't think that doesn't prove anything. You can probably produce a jet even just because we don't have the model run on the computer doesn't mean that it's impossible. I don't know. I used to be very excited. I used to work with Shahar, actually. The way we got into this, I think both of us, was from the study of high spin black holes. And I'm definitely guilty of having written papers saying, oh, look, like this paper in astrophysics says M87 has a spin of 99.9%. And there are such papers, and I cited them. And then I became more of an astrophysicist, and my astro friends said, there are as many measurements of M87 spin as there are teams measuring it, and you should not trust any of them, and so now maybe I'm a little bit extreme in the other side where I'm extra conservative, but I think the reality is we don't know. And that's actually one of the major reasons why we should do more experiments, because it's definitely possible to measure the spin, but we haven't done it yet. Okay, but any questions about delta, tau, and mu, or is it clear what they are? Okay, silence. All right, so now let me introduce gamma, the last one. So like I said before, if you have a flashlight in this photon shell and you aim the light ray in an arbitrary direction, it's not going to be bound. And in fact, light doesn't like to get trapped, and these orbits are unstably bound. They're unstable bound orbits. So if you have your flashlight on some shell, but then you aim it a little bit to the side, or you give it a little kick, delta R0, say, then the photon that you launch, instead of being perfectly bound on these unstable orbits, it will actually deviate from these orbits. And you can use the geodesic equation, in particular the geodesic deviation equation or the Jacobi equation, to show analytically in Kerr that the rate of deviation in radius is exponential. So if you give the photon a little kick off its shell, it's going to exponentially deviate. And after n half orbits, the radial deviation delta Rn will be the initial deviation delta R0, but exponentially increased by e to the gamma n, where n is the number of half orbits, and gamma is a Lyapunov exponent that controls the orbital instability of the photon shell. And gamma, like the other parameters, is a function only of the black hole mass and spin and the orbital radius. And I should say, this came out of a paper that Shahar was also on. So he's been here since the beginning of the story. Okay, so I've introduced the 4 special quantities, gamma, delta, and tau, that are intrinsically defined quantities that are properties of the geometry of orbiting light in the photon shell. And now I'm going to use that information to connect to what we see in images. And to do that, I have to describe how black holes lens light. And to do that, I need to describe how we set up an image plane to describe observations of a black hole. So there's a special coordinate system that was introduced by Bardeen in 1973. I'm going to describe it in words. It's not that complicated, but basically the origin of your coordinate system in the sky is the line of sight that points to the center of the black hole. And again, this is GR, so you have to be careful, but there's a way to make this precise. I'm not going to do this now, but you should think of the origin of the coordinate system as the line of sight to the center of the black hole. And then beta, the vertical axis, is the projection of the spin axis onto the plane perpendicular to the line of sight. So you have the black hole. This is your line of sight to the black hole. There's a plane perpendicular to the line of sight, and then you project the spin axis of the black hole onto your plane perpendicular to the line of sight. That defines the vertical axis beta, and then the perpendicular direction is alpha. That's all this is. And now you can ask, okay, you're sitting far away from the black hole, and you can shine your flashlight towards the black hole. So you can send photons backwards into the geometry. And the question is, what happens to them? All right, and so there's 2 very different behaviors. The first one is you shine your flashlight at the black hole. So you aim directly at the center of this coordinate system. Well, then the photon goes towards the black hole into the event horizon, never comes back out. At the opposite end, if you aim very far away from the origin, you're not aiming towards the black hole at all. So the photon that you send back into the geometry will come near the black hole, experience some deflection, but escape back out to infinity. So photons that are sent towards the image, towards the center of this coordinate system, are captured by the black hole, but photons that are sent very far away into the geometry escape back out to infinity. And then the question is, what is the boundary between the region of photon capture near the origin and the region of photon escape far away? And Bardeen in 1973 computed it. It's analytically known, and we now call it the critical curve. And it's shown here in red as this curve. This is again for a black hole of spin 94% observed from 17-degree inclination. And any photon that is sent within this critical curve will end up falling into the black hole and getting absorbed. Any photon sent outside of this critical curve will be deflected but escape back out to infinity. And the question is, what happens if you aim a photon exactly perfectly right on this critical curve? Well, it can either be absorbed, it cannot fall into the horizon, but it also cannot escape back out to infinity. And so the photons that are aimed exactly on this critical curve, they actually asymptote to bound photon orbits. So they come in from far away, and then they get gently loaded onto the photon shell and orbit there forever. And in fact, now there's a couple of observations. One has to do with going around the curve, and the other has to do with moving perpendicular to the curve. So let me start with the first one. If you aim a photon at a different angle around this curve, what's going to change is that it's going to be loaded onto a different radius in the photon shell. So what radius and which shell you load your photon onto is determined by the angle around your image plane. And that's really crazy. Think about this for a second. Because if you take an image of a star, when you look around the star in the image, you're also seeing around the star in the geometry. You change the angle phi in the image, changing the angle phi around the star in the geometry. But here, when you look around the image of the black hole, you change phi on the image plane, you're actually changing the radius around the black hole. And at any angle around this critical curve, the photon that you send will actually explore every angle. It'll ergodically move over the shell, but it'll just be at a fixed radius. So looking around the image is actually looking closer or deeper to the black hole, but at every angle. And that is the warped nature of space-time really in your face. The second observation is that this curve is an infinitely thin mathematical curve. And if you want your photon to actually orbit forever, you have to aim infinitely perfectly well on this thin mathematical curve. And that's the statement that these bound orbits are unstable. You can never actually have a photon go around forever because you can never aim a photon perfectly well on this curve. And so what becomes important to ask is, okay, suppose your photon is not exactly on the critical curve, but it's a little bit outside or within, at a perpendicular distance d from the curve. So slightly positive d means slightly outside the curve, and slightly negative d means slightly inside the curve. What's going to happen to the photon? And the answer is, well, if you aim a photon on this blue arrow at slight positive d, well, what's going to happen is that instead of coming in and sticking to the bound orbit at a fixed radius, it's going to be very close to that, but it's going to come in, skirt that orbit. It's going to hug it for a long time, orbit many, many times, but eventually it's going to escape back out to infinity. And if you send a photon with slight negative d on that arrow, then it's going to do the same thing. It's going to come in, orbit around the shell for a very long time, but eventually it will fall in. And so the takeaway here is that if you look at, if you shine photons very close to the critical curve and you follow their path backwards into the geometry, they're always going to end up in this photon shell tumbling around possibly many times before either falling in if they're within the curve or escaping if they're outside. Okay, so now that I've introduced this coordinate system on the observer's screen, we can get to the description of lensing in a little bit more detail. And the key point for us is that because light rays in the photon shell can go around the black hole multiple times, it follows that if you have a light source around the black hole, it can connect to an observer along multiple rays. And in this figure, which is taken from a paper with Shahar, actually, we're showing a single point source in an equatorial disk, which is shooting 2 photons towards an observer at 17 degrees far away. One, the blue photon actually shot downwards away from the observer, but bends back around the black hole. It does an extra half turn. And I'm going to call that an n=1 geodesic because it does n=1 half orbits around the black hole. And then the green geodesic is an n=2 photon because it's actually shot up, but then comes back down. So it does 1 orbit, and then it comes back up again, a second half orbit, so 2 half orbits total before reaching the observer. And in fact, you can prove mathematically that any 2 spatial points in a black hole spacetime are connected by infinitely many geodesics, null rays, that differ by the number of orbits around the black hole. It's quite intuitive. All right, so let me put it all together now. This is the most complicated slide I have, but it's not that bad. So just bear with me for a second. So I'm going to do the simplest setup, which is the one shown on the right. And that is, imagine you have a spinning black hole, and we're going to put the observer exactly on the spin axis. This is going to make the equations a lot easier. And then we're going to consider an equatorial source. So like the red dot in that equatorial disk that you see here. And like I said, we expect to see, if the dot emits in every direction light, we expect to see infinitely many images of the red dot. we're going to see an n equals 0 image. That's the photon that goes off the disk directly to the observer. That's what you would see even if there were no black hole. But because there's a black hole, there's an n equals 1 image that's actually emitted away from the observer, but then comes back up, and then an n equals 2 image, and n equals 3, and so on and so forth. And it turns out that you can solve the Kerr null geodesic equation in a large n expansion. This is not the large n of QCD. This is the large n of orbital number, but the equations simplify. And you can obtain an analytic description of successive images of an equatorial disk, say. And that's described by the equations at the bottom. And they're very simple equations, and they're illustrated by the color wheel on the left. So let me explain that. So suppose that the mth image of the disk that you see is the color wheel in the top left. That's the mth image that you see from photons that went around m half orbits. Now, of course, that's not an astrophysically realistic setup. It's just to illustrate the lensing behavior of the black hole. The black curve in the center of the color wheel is that critical curve that corresponds to the image of the photon shell. So the point here is that whatever the direct image is, that's described by the astrophysics of the source. You have to know the details of the accretion flow, the disk, whatever that is. But the point is, if you do know the n equals 0 image, the direct emission from around the black hole, then just from general relativity and the lensing behavior of Kerr black holes, you can predict the pattern of lensed images because those are just mirror images of the main emission. And given the mth image, you can predict what the next m plus 1th image will look like. And it's the same as the mth image with 3 modifications. The first one is an exponential demagnification. So the color wheel gets squeezed in towards the critical curve, and it gets squeezed in by an amount e to the minus gamma. That's the first equation at the bottom of the screen. And that makes sense because d, which is the perpendicular distance from the critical curve, is telling you that, if you remember this equation, in order to do one extra turn, you have to aim exponentially closer to these bound orbits. And that's exactly the explanation for this e to the minus gamma squeezing of the higher mirror images, which is that if you want to see the image of the disk from light rays that did an additional turn, you need to look exponentially closer by e to the minus gamma to the critical curve. So that's the first effect. And in this configuration, for a Schwarzschild black hole, which is not rotating, gamma is exactly equal to pi. So the squeezing effect is e to the minus pi, which is also known as Gelfand's constant, and it's about 4.3%. As the black hole spins up, actually the demagnification factor becomes less strong, and at maximal spin, it's only about 10%. So you expect successive images to get squeezed by 5 to 10%. That's the first effect, the demagnification. The second effect is that the image gets rotated. And you can see that clearly from the right, because the red dot, if it shines a blue n equals 0 photon that comes to the observer from the left side of the picture, well, the n equals 1 photon will actually come from the other side of the black hole. So it'll appear on the opposite end of the image. And if you think about it in 3D, that means that every point appears rotated around the image. And that's why the color wheel at the bottom left is rotated by exactly half a turn. So a rotation of pi or 180 degrees. And that's actually delta, which is exactly how much the photon went around the black hole in the additional half orbit it described. As the black hole spins up, the photons in this configuration get frame dragged with the black hole, so they rotate more. So this parameter delta increases until at maximal spin, it's almost exactly 3/4 of a turn. It's actually some elliptic integral function or whatever, but it's almost 3/4 of a turn. And then the last effect is that, okay, here it's a static image, but if you imagine the source is time dependent, then additional higher lensed images appear time delayed relative to each other. And the time delay is exactly tau, which is how much extra coordinate time it took for the photon to do its half orbit before reaching it. So the takeaway from this discussion is that, one, the parameters gamma, delta, tau, which are intrinsically defined in the geometry of the Kerr photon shell, actually control the lensing behavior of the black hole. And two, at least in some situations, you can see intuitively how simple it is. It's not that complicated. Now, okay, if the emitter is non-equatorial and the observer is off-axis, there's various correction factors, but morally, this is how it works. The details get more complicated, but there's nothing more mysterious happening. Okay, so now that was the technical part of the talk. I'm going to put it all together and summarize. So what do we expect to see around a black hole? Well, if you have a real black hole in the sky, there's going to be some hot gas around it. It's going to emit some photons. And most of these photons are not going to be aimed in a special way. And some of them will just come off the disk towards our telescope, and it'll give us an image of whatever is around the black hole. And that we're going to call the n=0 or direct image of the main emission. But some of the light will happen to be aimed just right to do 1/2 turn before escaping this photon shell and creating an additional mirror image of what's around the black hole. But because it has to be aimed just right, it'll be lensed into a narrow ring on the screen. And some of the light will be aimed exponentially better, but there'll be exponentially less of it. And it'll be able to skirt the photon shell for 2/2 turns before escaping, but it'll have to be lensed exponentially better into this exponentially narrower n=2 ring. And of course, this is E and M, everything linearly superposes. So the total image that you see is just the sum of all these image layers, the background n=0 layer that shows you what's around the black hole, and then superimposed on top of it are these additional layers, which are comprised of photons that orbited around the black hole and carry mirror images of the main emission. And there's the n=1 ring, and then the n=2 ring, and then the n=3 ring. And each of these rings get exponentially narrower. So you can really see the n=1 here, and if you squint, you can see n=2. This is on the left-hand side is a time-averaged image, where now you can see it a little bit clearer. The diameter of this photon ring is about 10 m in units of the black hole mass, and the size of the first photon ring is about m in width. And you can see it quite clearly. It's the first ring, which is about 10% in width of the diameter. And then within that, there's an even narrower ring, which is 10 times thinner and even brighter, and that's the n=2 ring. Now, as I said at the start of the talk, I think in response to Rami's question, maybe, we have not resolved the photon ring. So, for all we know, everything I told you is just science fiction. But we are confident in this prediction from general relativity, and it's been confirmed in state-of-the-art numerical simulations, like the one that you see here by George Wong, where you can take a horizontal cross-section of the intensity profile across the image and a vertical cross-section. Those are shown in blue and red on the right-hand plots. And you can see these spikes in the intensity profile, which correspond to the photon ring. And then you can zoom in on these spikes. That's the bottom right panels. And we've decomposed the intensity, the contribution to the observed image, into layers that correspond to photons that did a certain number n of half orbits around the black hole. And so you can see there's a background n=0 image. And then on top of that, there's a first spike, which is the n=1 image from photons that did half a turn, and then exponentially smaller. On top of that is the n=2 image, and then the n=3, and so forth. So these spikes, these photon rings, they get exponentially narrow in n, but they have roughly the same height, because as the ray passes through the emission region, it collects roughly the same number of photons each time. And that's the intensity or height, but the flux, which is the area under the curve, is exponentially smaller. So about 90% of the photons that we collect are probably direct photons. About 9% of them are n=1 photons, and about 1% are n=2, and that adds up. And then the rest, actually, there might not be more orbiting photons because of absorption effects. Okay, so let me summarize everything I've told you so far. It's a prediction from general relativity that embedded within a black hole image, there lies a thin photon ring, which is itself composed of the stack of subrings, which are self-similar because each subring is an image of the same thing. It's a lensed image of the main emission, and we can index the rings by the number n of half orbits executed around the black hole. And this characteristic lensing behavior of the Kerr black hole can be characterized by three parameters, gamma, delta, and tau, which respectively control the demagnification, rotation, and time delay of successive images, and therefore are observable in principle. These are fundamental constants of nature that are predicted by the Kerr geometry, which we could in principle measure. And the last thing I want to emphasize is that these subrings, they converge to a specific shape predicted by general relativity, that critical curve. And you can see that on the plots on the right-hand side. The peaks from n equals 1 to 2 to 3, they converge to the n equals infinity ring, which is the photons that orbit forever. That's the critical curve. And so we have an analytic prediction for the shape of high-order photon rings. And the low-order n equals 1, n equals 2 photon rings converge to it very rapidly. And that gives us a handle on the black hole's strong gravity, which makes a prediction for the shape of the observable photon rings. Okay, so that's all the theory. Are there any questions about what I've said, complaints, comments?
Sorry, but I do. Can you go back to the previous slide?
Sure.
So can you guide me through the scales here? Because I heard you say 10M. Here, yeah, presumably it's 94 again, so it's the horizon size is an M essentially.
Can you see my mouse now move or
Yes,
not?
I can.
Okay, so good. So from here to here, this is about 10M. Okay.
Okay.
So, okay, you can convert if you know, you need to know that. Okay, so in the sky you really see an angle, an angular size,
Right.
and you can convert from angular size in the sky to geometric units of the black hole mass if you know the mass to distance ratio. You need to know m over d for the black hole. But let's assume that we're looking at a simulation here anyway, so we know everything we're doing, so we can use these geometric units. So the diameter of the ring is roughly 10M. And in the real world, what that means is that if you know the distance to the black hole, you can literally put a ruler across the sky, measure the diameter of the ring, and you know the mass. The width of the ring, of the n equals 1 ring, is of order m. It's about m. So this n equals 1 ring here has about a width to diameter ratio of about 10%.
So if I wanted to see this, so in these units, the size of the black hole is about the size of that n equal 1 ring, right? It's about m.
So size of black hole is
But I mean,
yeah, the horizon radius is r equals 2m if the black hole is not rotating, and goes down to m if the black hole is rapidly rotating.
but you said it's 0.94, right? So it's about
Yeah,
m.
so here it's like 1.2m.
So the horizon is about like a very small point here inside. No, that can
No. Okay, so all right, I see what's happening. So in the real world that we live in, when you see something somewhere, it's really there. And if it has a certain size, that's the size of the object. Okay, in this business, just because you see something somewhere, it doesn't mean it's actually there, because light can bend. And as a result of this, just because something has an apparent size doesn't mean that's the actual geometric size of the object. So first of all, if you have a ring of radius rs in the source, it's going to appear at an impact parameter b. So think of the radius from the center of the image, b, which is about rs plus 1. And if you have in the setup that I showed on the previous slide, where you're exactly on axis looking at an equatorial source, you can prove that this equation is exactly true in a 1 over rs expansion. Okay, so so this here in the geometry, you have the black hole, okay, and you have a disk of stuff, and this disk shoots off light. That's the direct n equals 0 emission. And that's exactly the light that you see in this plasma here. And so the end of this plasma, the last light that you see here, is the light that's emitted from where the plasma enters the horizon. And because in these simulations, the emission is near equatorial, what that means is that this shadow here, this dark feature, has a boundary, which is basically the intersection of the black hole event horizon with the equatorial plane. So it's this circle here, intersect the event horizon with the equatorial plane. That circle, its apparent image in the observer, in the image plane of a distant observer, will be basically this shape. And it has it's consistent with everything I've told you, because this has a diameter of about 5 m, which is a radius of about 2.5 m.
Okay.
And that's about 1.5 m is about the event horizon radius. So everything I told you is consistent. Does that make sense now?
Yes, I think so. I was wondering how an M turns into a 10M, and I think you explained it.
Yeah, so okay, the way to think about this intuitively is that the diameter is 10 m, which means this photon here off to the side was emitted with an impact parameter of 5 m, but that's our source of about 4 m. And if you remember, for this high spin black hole, I told you that the photon shell extends out to 4 m. I mean, it's not exactly this, but at the order of magnitude level, like the numbers roughly work out. You can think of it that way.
Okay, thanks.
Are there other questions?
Another question, yeah, I have another question.
Yeah, please.
You mentioned before that photons which are coming from the same location will go in different directions, and they'll have this different reflection, different number of orbits, and so on. And therefore, you argued that you will get different copies of the basic picture, of the basic structure. Did you estimate what happens to the frequencies? Because will they all have? They probably won't. I did do the calculation on top of my head, but they may have different redshifts, and even if they don't have different intrinsic different redshifts, they may be coming in completely different directions in the local plane. And if you're going, if you in a system like this, especially if you want to be in an optically thin region in order that the photons will not be absorbed, then the emission in different directions may be have a completely different spectrum and so on. So the images may not, after all, be replicas of the same thing. They may be.
Yeah,
They may be very different. Did you try to calculate it?
Yeah, I understand your question. It's a very good one. It's not as big of an effect as you might think. So let me explain. The redshift actually becomes huge when you approach the horizon. So that's why this boundary here is not very sharp. There's still photons escaping from, all the way here. But if you look just a little bit outside, these photons, they become infinitely redshifted. The last ones to escape are basically infinitely redshifted. And so it's true that the photons that you see at fixed frequency at the observer, as you get closer and closer to the horizon, in the source had to be emitted with higher and higher frequency. So the emission frequencies of the photons you're observing at your fixed frequency, the emission frequency varies very rapidly here, and it actually has to go to infinity as you approach the horizon. The redshift for emission from about 4 m, which is where the photon shell is, the redshifts are of order 1. So, like they're like 20%, 30%, 50%.
This is not what my question.
Okay.
I completely understand the redshift is infinite near the black hole. and it is not very large. What I was asking is, consider just a single point at a given location may be emitting very different emissions in different directions locally.
I
And
understand.
since you're seeing, suppose that you are standing there.
Yeah, no, I understand what you're saying now.
In one direction, you'll see your face. In another direction, you'll see your back. And your face and your back are not the same.
I think I understand what you're saying. So in this cartoon picture, it's important for me to say two things. One, that the red point source is emitting isotropically.
Yeah,
right?
but
Because
it is that in a astrophysical system, it may most likely not be emitting isotope.
I agree, but we're physicists. So let me start with spherical cow, and then we can deform. So for this picture to be exactly true, I have to say two things. One, that the red source emits isotropically, and two, that it emits the same across all wavelengths. Now, of course, in the real world, emission is not isotropic at all. It's beamed. And moreover, you're right to say that if the emission were monochromatic, if the emitter had a single frequency, then actually I could only see emission, and I only observed it at one frequency, then I would only see some emission in some parts of the image and nothing at all elsewhere, because it's not exactly the same frequency. Now,
Exactly, this was exactly my point.
Now I understand. Now, what's funny though is that that ends up not being such a big deal for all these simulations. And in some sense, it's an accident because of how synchrotron radiation works. And synchrotron radiation is broadband. It's very similar across many decades in frequency. So yeah, there is a synchrotron peak, but actually the peak is very flat for many decades in frequency. And so that's actually not a problem in these simulations, in these systems. You don't have to worry about that so much. I agree. In principle, you would have to, but if you go from 230 gigahertz to 340 gigahertz, the source doesn't really change in its emission pattern, for instance. And the redshift effects are much smaller than that variation. There are other astrophysical effects that matter a lot more, like absorption, for instance. That's what we were talking about earlier on. So I guess, let me say it this way. If you want to be very precise about what you're going to see, then all the details of the astrophysics and the geometry really, really matter. What we're trying to do with this photon ring effort is to identify universal features of black hole images, which are certain characteristics of the image that are independent is too strong of a term, but weakly sensitive on the details of the accretion flow, which is unknown, and on the details of stuff that we can't control. And I think, the positive way to look at this is that it just so happens that in these black hole spacetimes, if you have synchrotron radiation, which is very broadband, and you're observing at the frequencies that we're looking at, you do really get a full ring and not just like segments of the image illuminated and others dark. But yeah, it's because the emission is broadband. These are all great questions, by the way.
Thank you.
Thank you. Also, nice to see you again. I think we met for the first time a few months ago. Thanks for coming to the talk.
Well, pleasure.
Okay, so I'm already over time, which is totally fine. Let me wrap up with some slides. So everything I told you started with this paper that you can see Shahar's name. I think Shahar is the leading Israeli physicist working on black hole imaging, and hope there will be many more of you getting interested in this field. The details of some of the calculations I discussed are in these two papers, and I'm happy to share the slides or send you the references. I can't resist, because this is a gravity seminar, I can't resist sharing this connection to LIGO, which I think it sort of has been morally understood for a long time, but in mathematical details has only been worked out very recently. So I think everyone on this call recognizes what this is. This is the first LIGO detection. And you can see this waveform, which has an in-spiral phase, that's the slow oscillation. Then there's the coalescence or rapid merger phase, the nonlinear regime. And then there's this exponential decay via quasi-normal modes when the final black hole settles back to equilibrium and you get these exponentially damped oscillations. So hopefully this is familiar. But I want to show you this simulation from the Simulating Extreme Spacetimes project. So what we're seeing here is what happens in the underlying spacetime as the two black holes merge and produce the gravitational radiation whose waveform we just saw. So this is the in-spiral phase, which is slow. The black holes rotate around each other. And you can see spacetime ripples that disturb the background field of stars. And now the black holes have merged. And look, there's a ring around the black hole. Look at that ring. Let me play it again. So the black holes coalesce. It happens very, very fast. And right after they merge, now we have a single black hole. And this single black hole is now going to return to equilibrium very fast by shedding its hair via gravitational waves. And these last waves that come out, the late time signal, the last part of the waveform, consist of these ripples that go around this ring. Right? Hopefully it's clear on your screen. You can see the last ripples, they ripple around the ring. And so I've been telling you for the past hour about the photon ring, but really I was only looking at null geodesics of the Kerr metric. And that's because I'm effectively looking at high frequency photons, which I can treat as point particles. But I could also think of high frequency gravitons as point particles. And then I would have a graviton ring. And in fact, the last radiation that is emitted in a black hole merger, these so-called quasi-normal modes, are in a very precise mathematical sense associated with the photon ring, or the graviton ring, we might want to call it. And the reason is the following. When two black holes merge, you have a final black hole that's surrounded by energy that's rippling around the spacetime in the form of waves. And in the high frequency limit, you can think of these waves as collections of point particles. And the very last waves to escape are basically made up of particles that orbit around the shell a long time before leaking out. So this is not a coincidence. And with Shahar, we wrote this paper in 2022, where we made this connection mathematically explicit for the first time, really. There was work in the 80s by Ferrari and Machoun, who proved this connection for a Schwarzschild black hole. And then for Kerr, nobody really looked at it until 2012, 2013. There was a group at Caltech that said that this ought to work, but they didn't know about the photon ring, so they didn't make the connection that I'm about to tell you. That was 2 years ago now. So the spectrum of quasi-normal modes, these are the characteristic frequencies of the black hole. So when it settles to equilibrium, it emits at a characteristic range of frequencies. I think everyone here knows that. The spectrum is labeled by 3 integers, L, M, and N. L and M are like spheroidal harmonic numbers. And N is an overtone number, which is positive. And in general, the spectrum of quasi-normal modes of a Kerr black hole is extremely complicated and does not admit an analytic description. You have to solve for it numerically. But in the Eikonel limit, or high frequency limit, where the waves can be approximated as null congruences of point particles, then it is possible to obtain an analytic approximation. And that's what you see on the screen. So when L, which is basically the angular momentum, gets large, the frequency also gets large. So this is high frequency or high angular momentum. And then basically there's a leading term, which is linear in L. That's the L plus a half times the coefficient omega real. And then there's a subleading term, which is order constant in L, which is purely imaginary. And that's why the modes are exponentially damped. And it's minus I times the overtone number. And then there's another coefficient, gamma L. And I can't resist explaining to you in detail how the spectrum of quasi-normal modes is exactly controlled by the photon ring parameters. So for instance, let's take gamma L. It's a function only of M and L, the integers that label the spectrum. Well, as you remember, M goes from minus L to plus L. It can take 2L plus 1 values. So m over L is always a number between -1 and +1. And it turns out that the imaginary part of the quasi-normal mode frequencies, the damping, this gamma L, the way you compute it is if you give me a given L, I just take the ratio and call that mu, and I find the photon ring radius, the orbital radius, which has that mu, that signed inclination. So that picks out an inclination of an orbit, and therefore an orbit. And then the Lyapunov exponent gamma of that orbit divided by the orbital period of that radius, gamma over tau, gives me the imaginary part of the quasi-normal mode frequency. And then the real part is basically the angular momentum or orbital frequency of the photons. So I think at first sight it's quite remarkable, but then when you think about it, it's mathematically clear and physically intuitive that the quasi-normal modes that a black hole emits are associated at high frequencies with waves that are sticking around in the photon shell before leaking out at late times. And quantitatively, you can use the photon ring parameters to predict the spectrum. And I should say that LIGO can see the L equals 2 quasi-normal modes, and with LISA, we think we'll be able to see some L equals 3 modes. This approximation is an expansion in 1 over L, which has about a 10% error at L equals 3, and it is basically perfect at L equals 4. L equals 4, of course, will not be seen with even LISA, I think. But in some sense, if you took high-resolution images of a black hole and compared successive images, you could measure gamma and delta, and in some sense, that would be a window into the high L spectrum of quasi-normal modes, which I think is really cool. All right, and now the last thing I will say is an experimental proposal that has been put forward in these papers for how to actually go out and resolve the photon ring with a single satellite, measure its shape, and figure out something about gravity using this. So, of course, I would have to go into the details of interferometry to make this precise. I think some of you already know interferometry, and it would be redundant, and others maybe don't know, and I don't have time to explain it. But the key idea is that the way we see black holes with the EHT or its future extensions is not the way that you and I see things with our eyes, or our phones take pictures with our cameras. We don't see the image directly, but we see the Fourier transform of the image. So really, it's all about Fourier theory. And what I'm showing here is the top image is just a hole in a disk seen from above, where I've turned off strong lensing and there are no photon ring images. And the bottom left image is the same image, but with strong lensing turned on, where I'm allowing myself to ray trace orbiting photons. And then you do get the n equals 1 and n equals 2 photon ring and so forth. And then on the right-hand side, what I'm showing is array at different angles in the Fourier plane of the Fourier transform of the image. And that's called the radio visibility, and that's the observable that an interferometer directly samples. And the key point is that if you have an infinitely thin ring in 2 dimensions, its Fourier transform is a Bessel J0 function, which oscillates forever. But if you have a thick ring, then basically it's only going to oscillate up until you can resolve its width. And then once you've resolved out its width, you've resolved out the signal, and the power dies off exponentially fast. So intuitively, the key thing to take away is that if your image in the sky is the top image, which is just an n equals 0 image with a hole in a disk, you have a very thick ring. And once you go to long enough Fourier frequencies to resolve the thickness of the ring, to be able to tell that the ring is not infinitely thin, but it has some particular width, the signal dies off. But if you have also the photon ring on top, it consists of rings that get thinner and thinner and thinner. So it's like you're in the infinitely thin ring regime, and then basically the Fourier transform rings forever. And the x-axis on these plots, if you fix the observation frequency, then you should think of as the distance between the telescopes. And the Earth diameter at the current observing frequencies is about 10 gigalambda. So basically, with current observations at the EHT, we can only see up to here. So you can only see this first null and then the start of the hop. And indeed, we do see this in the EHT data. But notice that that's consistent with both the image on the top and the image at the bottom. And that goes back to the comment I made to Rami earlier at the start of the talk. So we have not resolved the photon ring, and we cannot conclude that it is present in the image, because what we see is this hopping, but we only have one null, which is consistent with both images. So what we really need to do is to go out here at 40 gigalambda, and at current observation frequencies, that's about MEO or GEO. But because we're going to go higher frequencies also a little bit, we can get away with an orbiting satellite in MEO. And if we park our satellite there, then we should see either this signal or this signal, and then we can really tell if there's a photon ring or not. So that's the first thing we want to do. But more than that, it is not obvious, but it's true, and we showed it in these papers that I was mentioning before here, that the ringing of the Fourier transform of the image, the radio visibility, which isn't observable, has a periodicity which is set by the diameter of the ring. So how does it work? This is the slide, the last slide that I really want to show. So imagine you have a satellite that's orbiting around the Earth in the plane perpendicular to the line of sight to M87. It turns out that at every angle phi around the orbit, you're going to measure some ringing pattern in your interferometer, this radio visibility. And the periodicity of that ringing is 1 over the diameter of the ring at that angle in the image. So if you have a satellite orbiting around the Earth, at every point around its orbit, it measures some ringing, and the periodicity of that ringing gives you a diameter, which is the diameter of the ring at that angle. And if you let the satellite complete a full orbit, and then you come back again, another orbit, every time it orbits around, you do another measurement of the diameter, angle-dependent diameter of the ring. You can average the observations and lower the noise and get a better and better measurement. And at the end of the day, you can say, okay, what's the shape of this ring? What is d phi? The diameter is a function of angle. And it turns out that the Kerr metric predicts a very special functional form for this, which is shown here. So the size of the ring and its shape depend on the black hole mass, spin, and the observer inclination, but also the astrophysics. And this prediction has 3 parameters, R0, R1, and R2. So obviously they depend on the mass, spin, and inclination of the black hole, but in a way that depends on the astrophysics. So we can't predict what R0, R1, and R2 are, but we can predict that the shape has to have this functional form if the black hole is a Kerr black hole. And for measuring R0, R1, and R2, it's a complicated story, but you can infer the mass of the black hole and its spin and its inclination. So that's what we want to do. And we have had this effort over the last year now that's really accelerated in conjunction with NASA and various partners around the US and the globe to develop this space mission, which will be proposed next year for the next NASA SMEX, or Small Explorer mission, which is the next NASA mission that's going to fly in 2031 and is slated to have a budget of $150 million for the instrument. That's excluding launch and operations. So we went to NASA and we had a workshop there. We met their team and their engineers. And this is the kind of antenna that our satellite would have to work. And we're now hard at work with a lot of postdocs and students to forecast the kind of observations that we could do. Here's some technical numbers. I'm happy to talk about it if you care. But the point is, we could make movies with very high resolution in which we resolve the photon ring and we're able to confirm its existence and infer the parameters of the black hole. So this mission is called BHEX, the Black Hole Explorer. Will actually achieve the highest angular resolution in the history of astronomy, detect the photon ring, measure black hole spins, and the technology that would enable this is absolutely unbelievable. We would have the highest ever downlink from space using laser downlink of 100 gigabits per second. Actually, just last month, Lincoln Labs tested their T-Bird from low Earth orbit, which downlinked 200 gigabits per second into NASA Goddard. So this technology really exists and it works. And there's a lot of really cool engineering stuff that I'm happy to tell you more about, but I'm way over time. So let me conclude here. In summary, I hope that you now understand what the photon ring is from a theoretical perspective, and that you're excited about the connections to experiment and that at least BHEX is on your radar. And if anyone asks you what is the next NASA mission that you hope will be selected, you'll be able to say BHEX, or at least understand why many of us are spending our time pushing for this. Thank you for your attention.
Thanks, Alex, for a great talk, as always.
Yeah, sorry I went a little over time, but there's a lot of discussion, and if you have to go, please feel free to go. And if you
Yeah,
have
of course,
questions,
anyone who needs to leave.
I'm happy to hang out.
So we had a lot of nice questions, but any more questions? Okay, we had quite a lot already.
Yeah.
All right, so let's thank Alex again.
Thank you.
Thanks.
Thank you, Alex.
Yeah, Robbie, if you have any other questions, now's the time.
I know.